full screen now? Do you see the full screen?
Yes, you're good.
Okay. Okay, great. So I'm just going to do a few highlights from Jim Stone and Jonah Miller's talks from Wednesday morning about radiation transport and neutrino transport in simulations. And I wish I had the slides. Sorry, I didn't have enough time to contact Shane directly, but Shane also led some discussions on this point. But I think the discussion talks were not up on YouTube, so I didn't grab those. But if Shane's still around, he can add whatever he wants to here. But I do want to comment again on how great it's almost been like a hybrid conference where we've been meeting over a number of different platforms between the Zoom, Slack, Twitter, and YouTube. So I know that can be kind of cumbersome for a lot of people switching back and forth between us, but I really have found like once you get the hang of it, there's some really nice advantages, like being able to go back and catch a slide that you might have missed or wanted to spend more time on. Literally catching the words of the speaker again for clarity has been very helpful, especially for these kind of summary discussions. Right on my slide. Okay, there. So Jim Stone started with the the real basics of what is radiation transport and how do we go from essentially the full radiation transport equation in all its four-dimensional time-dependent glory or four-dimensional space, time, and then also frequency and angle dependence, right? Many dimensional problem, and points out that, right, this term in the integrand is ultimately what we're trying to calculate. And as you pointed out, calculating this distribution function over all of phase space is what's so challenging, right? Because it is multi-dimensional and time variable, and basically just impossible to completely resolve numerically. So then he kind of went through some of the main techniques that are being used in the field these days to break down this problem of solving for I sub nu as a function of angles and spatial positions into into something that's more manageable. So again, just a couple of the highlights. Here's a summary of the M1 closure method, which is has been very popular, especially in our field, our immediate field of radiation, MHD, dynamics, and GR applications. It seems to work relatively well in GR as opposed to the flux limited diffusion, which has some problems in relativistic setting. So anyone who's actually tried to apply such a method in practice knows it's not exactly trivial, but it's not intractable. And you can do it, and you can run it with most of our current MHD codes. The question then though becomes whether you get the right answer or not. So it highlights, this is a nice visual example of the ray collision problem, right? Because you're kind of treating these photons as a fluid with vectors, right? Or with moments, I guess. When you add them, when you add them together, their vector components can cancel out, and you get these kind of funny effects where crossing beams add up to like the average beam, and you get funny shadow effects. So this is really an extreme example of where the M1 method can go wrong. But Jim raised an important point about this also, is that we can construct such an idealized situation, but it's not really clear yet whether this this situation is all that common, or when it does exist, how bad does it really throw off the problem, right? Like all of these methods, it's going to come down to a cost-benefit analysis. Whether which of the methods is most problematic or most efficient, most useful, and we have to, can't let the perfect be the enemy of the good. So here's another popular method that's I would say its stock is currently rising. There are a number of these very successful and publicly available Monte Carlo codes, which have been applied both for photon transport and neutrino transport. And one of the nice things about them, as we highlight here, is not just that they're simple and easy to incorporate. I would say probably like one order of magnitude easier to implement in most codes than the M1 closure, except possibly in highly parallelized architectures. But Jim raised a very important point here, which I'll admit to being very guilty of, kind of poo-pooing the numerical noise of Monte Carlo, saying, this is astrophysics. We don't need to get the exact right solution. Anything, you want to match your numerical accuracy to your observational accuracy, or else you're just wasting cycles. But in the case of radiation dominated flows, right, this becomes a lot more important, right, because these few percent fluctuations due to the Monte Carlo numerical noise can actually amplify and generate real significant noise in the form of waves or turbulence in the system that are really non-physical and could really throw off your entire answer. So that's something that I personally took away as a very important lesson from Jim's talk that we'll have to keep in mind when we try these methods in the future. I personally am more in the Monte Carlo camp. Then he also raised the point of tests being very important. I'll just reiterate a comment that I made during the discussion. There is that, right, Jim pointed out that there are relatively few and maybe overly simplified analytic tests for these numerical methods. And I just want to point out that we all have computers now. We don't need to rely purely on analytic tests, but we very much should rely on, as a community, on tests and on some universal tests that we can use to both compare codes and develop new codes. And I think this will also help, one of the important problems in the community where these codes are very difficult, very large scale, and can be seen as, something of, black boxes and dark magic. And that's something we would very much like to get away from, both in our community, and I think we see this over and over again in the scientific community as a whole, that theoretical work and computational work is moving in the direction of, you have to have reproducible, shareable codes in order to really be doing good science. And that's, I think that's a point that can be raised here. So then moving on to Jonah's talks about the neutrino transport. So this is just his starter about how it's, it's kind of relevant both in the core collapse supernova, which is shown on the right, where you have a collapsar and then a kind of an accretion disk inside of the star that then has to blow out to form the supernova, or on the left, the neutron star mergers with the tidal ejecta, the winds, the torus, the ejecta torus around it, and the disk. In all of these different cases have different levels of emission, absorption, optical depth. So neutrino transport is both important and highly non-trivial. It goes over, there are a lot of, wide range of different schemes for these different scenarios, just like photon transfers, a lot of the similar ones, particularly popular recently. And in our collaboration, we're trying some of these leakage schemes, which kind of get to the point which I think we made during Shane's discussions, that one important difference between the neutrinos and the radiation is that while they both affect the dynamics, really only the radiation is ever observable. So, it's good to think of leakage schemes as something that really is a pure dynamical force as opposed to any observable force. Here's just a nice slide that Jonah posted that I very much like, and I'm publicly stating here that I'm going to probably try to reuse this line, even though I generally try to avoid putting equations into my talks. This just highlights just how difficult the problem it is, and gets to that question of how, from an outsider, these all can be seen as dark magic. And I think as a community, we have to be more cognizant of this when we are giving our own talks, that we're reaching out and we want people to trust our work, and part of that trust, unfortunately, as we see in the broader societal response to science right now, it has to be transparent. We have to make it not seem like we're doing this dark magic that only we understand and then only we can do, and you just have to trust us. That being said, it's a great line, proof by intimidation. Here's another nice result from Jonah and the simulations with neutrino transport, is that we see that over a wide range of accretion rates, the actual angular dependence of the electron fraction seems to be, if not like totally universal, some very very widespread or characteristic trends over a wide range of initial conditions, where you have high electron fraction along kind of the 0 to 45 degrees, and then from 45 to 90, very low electron fraction, and how that directly feeds into the kilonova debris, and whether you see the red component or the blue component as a function of time. So hopefully, as we get more events like 170817 from different viewing angles, we'll be able to really probe this paradigm more fully. And I think that's what I had to say.
Thank you, Jeremy. I think that's a very good summary. And we're first, again, let's thank you by clapping, everyone. Jeremy talks. This was a very nice review. And by the way, I might actually borrow that slide too some point. I think it was very nice to summarize these equations in one slide. And so we're ready for questions for Jeremy or a discussion. Okay, so waiting for people to warm up for the discussion. I may have, I see a question, Julian.
Well, this is more of a comment than a question. And it's in regard to M1. Like many of the various closure approximations that try to solve the transfer problem by diffusion plus in some fashion, M1 is fine in regions of large optical depth and gets problematic as you go towards small optical depth and even optically thin regions. So almost by definition, the place where the results will be questionable is in the optically thinner regions. And so its evaluation as a useful method or a not useful method has a lot to do with how important those regions are. So if you care about outflows of modest optical depth, then you worry about it. If you're looking at situations where the photons are all buried, then diffusion is wonderful. And the way to, I think, be where the general rule about when to be wary in those regions of low optical depth is that its fundamental approximation is that the angular distribution of the radiation is axisymmetric around the mean flux direction. And that's a very strong assumption. You can easily imagine quite different angular distributions that where this modest optical depth region is important could have very different properties if treated precisely rather than with that approximation. And the collision problem is one vivid example, but it's certainly not the only one.
Right, and I think these are the kind of questions that, you know, we can say very qualitatively now, but it will be nice to get to a kind of more quantitative definition of these issues through, you know, kind of these universal tests or comparison approaches.
Yeah, I do agree about this. Actually, very, very much, because this is a community that is, well, not new to TEST, obviously, but compared to the numerical activity community, which is probably, you know, maybe been working on the binary black hole problem for longer, where we have really come up with a series of tests and code comparisons. It hasn't really been done at such a large scale. So it is something that need to be encouraged.
Yeah.
So,
Well, the EHT code comparison.
Yeah, it's a start.
It's a step in the right direction.
I agree.
But I think the problem with that one was, I think what they did in practice was, you know, mostly agreed, and then where the codes disagreed, you know, they dedicated a paragraph or two in the paper to explain why the codes disagreed, called it a day, published the paper, and moved, you know, everyone went back to their, you know, typical approach. That's not really a very useful approach for code comparison. You have to go in with kind of like pre-written rules about what you're going to do if the codes don't agree, right? Yeah, it's not simply to compare them. You have to also have some actionable items on that.
Now, point well taken, and I've been advocating for quite a bit now for the same thing, and I will probably be in touch with some ideas with this community on what to do, and then we can maybe have discussions about whether we can have something.
And as Scott mentioned, in a different context, you sometimes have to worry about the areas where the codes do agree and ask, is that only because they share the same assumption?
Yeah.
Yeah.
But this is one of the things that we learn also through our TCAN, that we do require, you know, to build in a lot of self-consistency among all these codes, or it's very difficult to make them agree on some of the maybe on the results, but not on the numerics for sure. So, okay, so I think we are ready to go for the next talk. I think we're going to be talking with Josh Faber next.